This is Neil from Anabit, and welcome to making high accuracy current measurements with a shunt and an analog to digital converter, or ADC. Okay, here's an overview of what we're going to cover in this video. First off, we're going to look at a typical high accuracy, high resolution current shunt measurement circuit and talk about some of the key parts. Then we're going to do a deep dive into current shunts, or shunt resistors, or as they're sometimes called, sense resistors, right? I'm going to use the word shunt throughout this video. But we're going to look at how do you size them correctly from a power handling and resistance standpoint. What are their specifications? How do they react with temperature and self-heating? Then we're going to do an example accuracy calculation or tolerance calculation. And then we're going to talk about how to connect your shunt to get the most accuracy in your shunt measurement. Then we're going to take a break from the text and the slides and look at a demo. And for the demo, we're going to use Anabit's open source precision multimeter reference design. And the reason we're going to use that is because it takes into account or uses a lot of the concepts that we cover in this video. Then we'll come back and we'll look at some considerations when picking out an amplifier for making accurate shunt measurements, and then also some considerations when choosing your ADC and ADC circuit for high accuracy current shunt measurements. All right, let's dive in. Okay, here's an overview of a high accuracy current shunt measurement setup. And I put there on the top right, just in case people don't understand how shunts work. I'm assuming most people do. But the idea is we're using a shunt to measure current. And we do that by taking a shunt which has a known resistance. We let current flow through it. We measure the voltage drop, and that way we can calculate the unknown current. Or in this example setup, I have a low side shunt configuration, and that just means the shunt is connected between the load and ground. Low side setups are nice because you don't have to worry about high common mode voltages. But sometimes that's unavoidable, so you have to use a high side shunt, which means the shunt is going to be connected between VCC and the load. So the first thing we want to do when we're trying to measure our shunt is we need a differential connection. We need to make sure we're measuring the voltage drop across the shunt resistance and nothing else. And that lends to using a differential type setup. A lot of times that's why we use the op amp, because we can take that differential input of the op amp, which op amps by nature have a differential input, and convert that to one output voltage that represents the difference in voltage between one side of the shunt versus the other. Then we can measure that with an ADC. Now, what's not being shown in here is there's typically filtering in there, whether that's filtering for high frequency EMI stuff, charge bucket filtering for the ADC, or anti-aliasing filtering. We're not going to get too much into filtering in this video, but be aware that it's typically part of the setup. And then another thing that's important about the setup is sizing. And we'll talk about sizing throughout the video, but sizing the shunt with the right resistance, sizing the amplifier to have the right gain, and then sizing the voltage range of the ADC to maximize resolution in our measurement. So let's start off with talking about sizing from a resistance and power sizing standpoint. So when we're choosing a shunt, ideally we want a high resistance value shunt to get a good voltage drop. And what is a good voltage drop? Well, it'd be great to have a voltage drop of 1, 2, 3, or 4 volts across our shunt because that level of voltage is easy to measure. It's much easier to measure 1 volt than it is to measure 100 millivolts accurately, or 10 millivolts accurately, or 1 millivolt accurately. But the challenge with using a high value resistance shunt is you get voltage drop across it and power dissipation, right? So let's look at an example of why we can't just choose a very high value shunt. So let's say we need to measure current in a range of 1 milliamp to 1 amp, so a pretty wide range of current. And we're considering a 1 ohm shunt and a 0.1 ohm shunt. So if we look at the 1 ohm shunt, we get the better voltage drop. We get 1 volt to 1 millivolt voltage drop across the shunt for our current measurement range. But 1 volt is a lot. Let's say we're working with a 3.3 volt circuit, right? If we drop 1 volt across the shunt, that's probably going to cause some of the circuits or microcontrollers that are in that circuit to reset if we're dropping as much as 1 volt from a 3.3 volt bus. So that's probably not going to work, even though it gives us a nice solid voltage signal to measure. If we look at the 0.1 ohm shunt, the voltage drop across it's going to be 0.1 at 1 amp, and it's going to be as low as 100 microvolts at 1 milliamp. Now, 100 microvolts is not easy to measure, but the good news with this setup is 0.1 volts If you take that from a 3.3 voltage bus, that gives us 3.2 volts. Chances are that's not affect the ICs or parts of the in our circuit. The second choice is probably the most logical if we don't want to cause issues in our circuit. And once again, choosing the exact resistance really depends on your setup, but the idea is we can't afford to drop a lot of voltage. The other thing about sizing a shunt, besides just the resistance, is the power rating of the shunt. The power rating of the shunt is just its max current squared times resistance, right? So that's the max current you can get through it based on its resistance. Because self-heating can cause errors in shunts, and we'll see an example of that, the best thing to do is pick a shunt that has a much higher power rating than what you actually need. That gives you a lot of margin and ensures that you won't have a lot of self-heating in your circuit, which we'll see soon causes error. The trade-off, though, of course, is the higher power shunt, typically the more expensive it is and the more room it's going to take up. Okay, let's talk about some important shunt specifications. So the big one is the tolerance of the shunt, or sometimes it's referred to as the accuracy. And this is just a plus minus, typically in percentage of the shunt's value. The other one is temperature, and this is the one that's overlooked. So the spec related to this is typically called temperature coefficient of resistance, or TCR. And it's typically given in parts per million, or ppm. Parts per million per degree Celsius, I should say. This spec actually has two parts, right? It's the ambient temperature where the shunt's being used. So let's say there's no self-heating in the shunt. If I'm using the shunt in an ambient temperature that's higher than the temperature it was calibrated in or tested in, which is typically 25 degrees C, might be 23 degrees C, but it's typically 25 degrees C. What is the difference where I'm using that shunt? And that difference leads to basically some error based on the TCR specification. Then the other thing you need to worry about is self-heating, because that's causing the shunt's temperature to change. Self-heating is caused by current flowing through it. That's why I was suggesting you want to size your power rating of your shunt with some margin, because it reduces self-heating, which increases the measurement accuracy of your shunt. Now, the self-heating spec is hard to get, or it's hard to quantify. Like, if I put so much current through my shunt, how much does it self-heat? Well, there's a couple different ways we can calculate that. The first is just by measuring it directly, right? So you could pump the max current you're going to use on that shunt through the shunt, and you can use a thermocouple, or you could use an infrared temperature sensor to measure the temperature rise through the shunt, which will eventually stabilize at some stable value. And that's where you could get the actual self-heating effect. But that is kind of tedious. The other way is to do a calculation based on the shunt's thermal resistance, which is a lot of times shown as an omega, and it's basically Celsius over watts. And this is actually a spec you see with a lot of electronic components, but a lot of people don't have to use it. For the shunt, though, it becomes important if you want to do this self-heating calculation. The problem is a lot of shunt manufacturers don't even provide this spec. But we'll look at a way based on other specs they do provide of how to calculate it. Okay, so here's where we start to get into the math. And this probably looks pretty math heavy, but this is what we need to do if we really want to understand the accuracy of a shunt. So I'm going to use an example shunt, and I'm showing the part number up there from Ohmite. It's an LVK series shunt, and I'm not going to read out the whole part number. But it basically is a 0.1 ohm shunt, and it has a power rating of 0.5 watts. And its tolerance from the data sheet is 0.25%. And its TCR is 50 parts per million per degree Celsius. So what is our accuracy, or what is the error of the shunt if we are measuring a 1 amp current in a 35 degree ambient temperature environment? So the first thing we need to do is we need to calculate our two error contributors. But the one that's tough to get is the self-heating one, because this shunt does not give us a thermal resistance specification. So let's look at this shunt's data sheet to kind of talk about how we can estimate what that self-heating specification is. We're looking at the data sheet for the shunt, and I sort of highlighted the one we're looking at. And you can see there's the power rating. Our range is 0.1 ohms, 50 parts per million for the TCR, and the tolerance of the shunt value is right there. Now, like I said, this doesn't give us a thermal resistance specification that we can use for calculating self-heating, but we can use this derating chart to do an estimate of the thermal resistance. So if you notice, this shunt is 500 milliwatts, but they basically tell you it can only handle 500 milliwatts to 70 degrees ambient temperature. They're saying once you get above 70 degrees ambient temperature, then you need to start derating the power handling of the shunt until you get to 0, which is the max environment you can use the shunt in, or 125 degrees C. So we can use this to basically create a slope equation to get our thermal resistance. And our slope equation will consist of the power, which is 0.5 watts to 0 watts, and the change in temperature. So delta power, delta temperature, which is the temperature is 125 minus 70, which would be 55 degrees. So we're going to use a slope equation to estimate our thermal resistance. Okay, and that's what I'm doing here in the math. So we have delta T ambient and delta P to estimate our thermal resistance spec, which is 110 over degrees Celsius over watts, I should say. There's our delta P, 500 milliwatts, and our delta T, 55 degrees. So now we can estimate our self-heating at 1 amp. And the way we do that is we get the power drop at 1 amp. So we take our thermal resistance spec and multiply it by the power drop. So if we have a 0.1 ohm shunt resistor and we have 1 amp, that's going to give us a power of 100 milliwatts. And that works out to be self-heating of 11 degrees C. Okay, so you can see this is the hardest part to get. Now we can calculate our total TCR error by multiplying our parts per million spec, TCR spec, by first our change in ambient temperature and then our self-heating temperature change, right? So remember, I said we're going to be using this in a 35 degrees C environment. If the shunt was tested at 25 degrees C, that's a change of 10 degrees. And then we already have our 11 degrees, which equals 21 degrees, times that by 50 parts per million, we get 1,050 parts per million. So now, using our tolerance spec and our TCR spec, we can now get what is the error or the tolerance of that shunt. So at 1 amp, I'm going to multiply 1 amp by our two percentages that we calculated. And so we multiply 1 amp by this, and we basically gives us plus or minus 3.55 milliamps. So that's the tolerance of our shunt based on the conditions we're using it in. Now, we can increase this accuracy in a couple ways. We could actually get a very high accuracy measurement device and get the real resistance of the shunt to reduce this error factor. We could also use active cooling to reduce the temperature climb in our shunt to reduce that error component of the shunt. So there is ways to basically improve the accuracy of the shunt, but this is how we do it from the data sheet using the TCR and the tolerance specification. Okay, now let's talk about how we want to connect our shunt. So the important thing is when we're measuring the voltage drop across our shunt, we want to make sure we're measuring just that shunt resistance and nothing else. We don't want to be measuring leads. We don't want to be measuring the resistance of solder or pads on our printed circuit board. So that's where the shunt's sense connections come into play. So a lot of precision shunts will have 4 connections. So this is actually the shunt we just looked at in our example accuracy calculation. And it's the same shunt that I use on the Anabit's precision multimeter open source reference design. So you can see it has actually 4 connections. One of them is the current connection. This is where we connect the current to, so the current can flow through the shunt. And then the other one that's marked V, that's our voltage sense terminals. That's where we want to measure that voltage drop. By using those terminals, that helps us ensure that we're not measuring resistance in our PCB pads or solder resistance. We're just measuring the shunt resistance. So that's why these shunts have sense lines. Here's an example. So this is software used for PCB layout. And so this is actually a screenshot from the precision multimeter's design using the same shunt that's shown in this picture. And you can see we have 2 of the terminals are used for the current flow, and then the other 2 are what we use for our voltage measurement. And then these resistors and capacitors here are for filtering. So this idea, remember, is this path is very high impedance. So we don't get much current flow in there. The current's flowing from this end to this end, and that's where we're making our measurement. Now, some shunts don't have sense connections. So in that case, we're going to use Kelvin connections, which sense connections are Kelvin connections, but here we have to add our own since we don't have sense connections. So here's another example shunt from a design I worked on. So if you're not familiar with PCB layout, the red is the top layer, the yellow is the second layer. This is a 4-layer board. The orange is the third layer, and although I don't see any blue in here, blue would be the bottom layer. So this resistor right here is our shunt. And so you can't see it, but on the bottom layer, the current's flowing here through the shunt, and then the shunt connects to ground. So the yellow you see is our solid ground plane that's on the second level. Now, these are our differential Kelvin connections to the shunt that go to our differential input amplifier. And so the idea is we want to connect to the inside of the pads. Why? Because we don't want to measure the current flowing through the pads itself because the pads have resistance, right? So we're trying to avoid that by capturing that voltage right at where the shunt resistor connects to the board. So that's why it's connected this way. And this might seem trivial, but think about it. 1 milliohm, 10 milliohms. If you're using a 100 milliohm shunt, that's a lot of error. So that's why Kelvin connections or using sense connections is critical for high accuracy shunt measurements. Okay, now let's look at a demo with some of what we've been talking about in action. And this demo is actually nice because it provides a little reference for what I'm going to talk about next with the amplifier and the ADC. So what we're looking at is the precision multimeter from Anabit, which you can find on anabit.co. Here I have an ESP32 based Arduino that communicates with the board using SPI communication. This board can measure all kinds of things, right? It can measure voltage between 200 volts and negative 200 volts, plus or minus, DC or AC. It can measure resistance real accurately, but it can also measure current real accurately. And this circuit right in here is actually the circuit we just looked at in our example for showing these sense connections. Here's the shunt, here's some test points, here's our filtering, and here's our amplifier and ADC. Here we go, and first we're going to show a reference measurement, right? So I configured a source and I tuned it to basically output 100 microamps. So remember, 100 microamps being put across a 0.1 ohm shunt is only 10 microvolts of voltage drop. So then what I'm going to do is I'm going to pull that current source out of the instrument and plug it into our precision multimeter. So there we go. And we're going to go to my computer where I'm printing it out to the serial monitor. And we can see our measurement being printed out. Notice the great accuracy we're getting, right? So we looked at this on a $4,000, $5,000 instrument, and now we're looking at it on this board that cost, $80. We're seeing 100 microamps or 101, 102. So we're only seeing about 1 or 2 microamps of error in this measurement. So to do that, we had to do a lot of what we talked about, right? We had to understand the actual resistance of our shunt that we're measuring. We have some filtering to take out noise, and we're not actually measuring that low-level voltage directly with the ADC. We're actually using a very high precision amp to boost that voltage up to a more measurable level. So that's how we're getting this great accuracy in this setup. Now, what I want to show next is the effects of temperature rise on the accuracy. So now I'm going to up the current source to about 1.5 amps. So we're going from a very low current to a much higher current. And what I'm going to do is I'm going to reset the serial monitor, and there's our higher amp value. And you might be able to notice, but notice how the value is slowly creeping up. So I'm going to pause it right there. But the idea is the current flowing through the shunt, which is right now at about half its rated power. At 100 microamps, it's at a very low power, so self-heating basically doesn't come into play. But when we shove a higher current through it, that's when you can see the effects of self-heating. And remember, when a material heats up, its resistance goes up. If our shunt resistance goes up, the voltage drop goes up. Well, if the voltage drop goes up, the calculated current also goes up. So we can see that our current starts out, we're only looking here in the microamp range, but here we have about 693, 727, 743, 749, 751, so on and so forth, until it sort of levels out, right, in this 59, 60, 62 range, right? So it self-heats and then it stabilizes once it, the heat and along with the outside temperature reaches some kind of equilibrium. So even though this has very little effect, we can kind of see that self-heating effect when we use currents that are closer to the power rating of the shunt, which once again, try to get a shunt with a lot of power rating margin to avoid this self-heating error. All right, now that we have seen our demo, let's talk about configuring our amplifier for our shunt measurement. Now, why do we typically want to use an op amp in this setup? Well, there's multiple reasons. You get a nice high impedance. You can kind of buffer between filter stages. But the main reason is these op amps have differential inputs. And that's what we need to make sure we're just measuring the resistance of the shunt and not, a single-ended measurement where we have ground plane resistance that is going to cause error in our measurement. So I'm showing a picture of an op amp configured for a differential input. And of course, the values of R that you set can determine whether it has a gain of 1 or a gain of 10 or a gain of 100, right? So I borrowed this diagram from allaboutscircuits.com. If you want to learn more about that, of differential amplifiers and how to understand their game, go ahead and check out that website. But we want to use our differential op amp, and it's going to output a voltage to our ADC. For the op amp, what are some of the specs we care about? Well, one of the big ones is offset voltage, right? So this is the voltage that is just present at the input of the op amp error voltage, right? And this spec, if you're using a very low-cost op amp, could be as high as 10 millivolts, could be 1 millivolt, could be 2 millivolts. If we have 2 millivolts, that can really affect our measurement. Think about the demo we just showed. We wouldn't be able to measure a 100 microamp signal if we have that much error because of offset voltage in our op amp. You also need to pay attention to gain specs, and that's a whole video in itself, but there's a lot of specs that affect or add error depending on your gain settings. Now, if we're configuring our op amp for some certain gain, we have to consider the resistors that we're using to set the gain, right? The resistors, just like a shunt resistor, are going to have some type of tolerance. They're also going to have some type of temperature drift. So be aware of that when you're choosing your resistors. And typically, you want to use thin film resistors. Next is metal foil resistors. They have very good temperature specs, but they're expensive. And then you can buy resistor arrays. So resistor arrays are typically made just for this type of application, differential op amp inputs. They have resistors based on some type of gain that you want. And the nice thing is they're all integrated together. So they have high accuracy, but they all drift in the same direction based on temperature changes. So they have really good temperature coefficient because if one resistor drifts one way, the other one's drifting the same way, so the gain doesn't change. But once again, resistor arrays are not cheap. Now, depending on the current you're trying to measure, there's a lot of different types of op amps you should look at. The first one is precision op amps. Precision op amps just have really good all-around specs, right? So pay attention, look for precision op amps if you care about offset voltage, low bias current, low noise, things like that. Instrumentation op amps are nice because they're made for taking very low-level voltage signals and having a high gain and being low noise. So if you're trying to measure a very low current, or I should say, a very low current that creates a very low voltage drop, an instrumentation op amp might be the right way to go if you need high gain. They also make op amps especially for current sense. So that's the exact application we're talking about. So these are another one to consider. Now, one of the differentiators of a current sense amp is that they're often made to handle high common mode voltages. And that way they can be used for measuring shunts that are on the high side that may have a high voltage so they can handle those high common mode voltages. If you don't need a high common mode voltage current sense amp, it may not be the best choice because sometimes they don't have the best accuracy specs. So current sense amps are great when you're dealing with high common mode voltages. And then finally, you have op amps that have built-in gain settings or programmable gains. I really like these because then you don't have to worry about the error contribution or calculating the error contribution of your gain resistors. They're integrated into the op amps package, and the op amps data sheet already takes those into account. And then what's nice about the programmable gain is this means the op amp will have some type of communication connection. Could be simple digital signal, could be I squared C, could be SPI, but you could change the gain in real time based on your current variant. Of course, the trade-off though for programmable gain amplifiers is they're not going to be cheap. Okay, and finally, let's talk about some of the ADC considerations for making high accuracy current measurements. So the first thing is you want to make sure you're picking an ADC with a resolution that matches the low-level current you need to resolve, right? And remember, when you're working with an ADC that has a high resolution, make sure that ADC and your circuit in general have the accuracy to back up that resolution. Accuracy and resolution are two different things, but they're related. So if you have bad accuracy, then you can't make use of your resolution. It gets buried in the noise floor. So first, let's talk about quantization error. So let's assume that our ADC has perfect accuracy. So the only error is due to its resolution or possible lack of resolution. So let's take a 14-bit ADC as an example. So let's say our 14-bit ADC has a 2.5 volt reference. So 0 volts to 2.5 volts is its range. The way we calculate quantization error is we take the resolution, which is 2 to the 14 minus 1. The reason we do minus 1 is because we're not counting 0. We divide 2.5 volts, our range, by that value, and then we multiply it by a half. The reason we multiply it by a half is worst case scenario, we're going to be halfway between one of the ADC codes. So this gives us 76 microvolts. Okay, that seems like really good resolution. But what if we're working with a shunt that's only 10 milliohms? That equates to 7.6 milliamps of error. So even at a high resolution of 14 bits, this is going to equate based on the shunt we're using to 7.6 milliamps of error. And that's just the quantization error, right? We're not talking about other error factors. A lot of times you're using higher resolution ADCs, 16-bit, 18-bit, 24-bit. The one I used in my example was a 32-bit ADC. The other thing you want to make sure you're doing is you're sizing the voltage range going into your ADC to your ADC's voltage range, right? And that's where having a gain amp and choosing the right resistance, setting your op amp gain and choosing the right resistance shunt comes into play, right? So if we have a maximum 1 volt output from our op amp based on gain and the voltage drop of the shunt, but our ADC has a 2 volt voltage range, we're essentially cutting our resolution in half. We go from 16-bit to 15-bit because we're not using that full range, right? So in that case, we want to make sure we use a voltage reference that's closer to 1 volt to match or get the full resolution of our ADC. Then finally, one way to really increase the accuracy of your ADC, but also your whole measurement chain, the amplifier and the ADC, is to do a 2-point calibration, right? So this is where we put in known voltage values across the range of the ADC, and we measure and we put correction factors in our software to deal with the error. That way, we can push almost all the error factors to the shunt. And if we're able to make a high accuracy resistance measurement of the shunt, we could basically get rid of most of our errors, and really temperature is the main thing we have to worry about. So once again, calibration can really help us reduce the error in our measurement setup. If you're not familiar with a 2-point calibration for an ADC and an amplifier chain, check out Anabit.co and go to the tutorial section where we talk about it. Okay, that's it for making high accuracy current measurements with a shunt and an analog to digital converters. If you have any questions, please use the comment section below. And if you have anything to add or you think I missed anything, please use the comment section below. You can also use Anabit's forum, which you can find on Anabit.co. Thank you for watching.